Oh, thank you, thank you.
Dad. Dad, he knows I have treats for him over here. He's like, what is going on? I want all the treats. Yep, going the other way. Yep, yep. Mhm.
I think you're more interested in this little thing you have.
Probably. Oopsie. No, I didn't see that. Yep, he's a little monster, so.
Nope, okay.
Oh.
Yeah. Okay, there it goes.
Danny?
Yes, ma'am.
Are we gonna have to label the rock types again? Or?
I will let you know exactly. I can't remember exactly what, I gotta go back and look at it.
I saw that you have like the 3 rock types, but not like.
It's major types. Yeah, it's not so much. Yeah,
Okay.
we're gonna go like over and over. We have a whole day of review, like nothing but review.
I turned everything into flashlights for me.
There you go. Did you see it's all updated now though? Like
Yes.
everything's in there.
Yes.
Yep.
Oh,
Yep.
that's interesting.
Oh,
So there's.
do I have anything to belong to you? Come over here.
Aw.
That's not what I asked you to do. That's what I asked you to do. Bang. That, bang. Stay dead. That, bang, 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 bang. That's be dead.
I'm a really.
Oh, you're terrible. Horrible at playing dead.
It's like I'm invincible. Ozzy, over here, Dickie. Oh, no.
You are a silly boy. Oh, who's your best friend now? Yeah.
Okay.
He's ridiculous. Yeah. You're ridiculous, dog.
So
You're
tell Ozzy
ridiculous.
bang. to follow.
Oh yeah, dog clothes.
Little elf costume.
Oh my gosh, that's funny. Oh my goodness.
But I was like,
Come on, bang,
Hobby Lobby has
bang.
Christmas stuff on
Yeah.
sale.
Yeah.
Off. I just saw this elf costume and I put it together.
Oh my god, that would have been hilarious. Right. Wait. Oh. Wait.
I'm gonna wash my hair.
That's my favorite expression. That one.
The pure dread.
The oh, think. Actually, the best is sit down, down, down. This is the best one when he looks away. Like I'm not going to look at it. I'm not. It's not there.
On each of his paws and his nose.
You can actually.
Oh,
Yeah.
poor baby.
He'll let you do it. Big little boy. Yes, he will.
No,
My goodness, this is torture. Oh my. What you doing?
Spreads them all over.
He's such a dork. All right. Yeah, stupid pet tricks. There you go. Okay. I think we're good. Are we good, people? Everybody situated? Awesome. Everybody eat lots of turkey? No? Oh, really? Outstanding. All right, well, we've only got like 2 lessons really before we start our review and then do our midterm. Woohoo! You're getting somewhere. So today is energy. All right. I have nothing else for you. Place. No. Come on. Thank you. Good boy. All right. So, and yeah, I see you. I don't know. All gone. Stop looking at me like that. He was very happy to see his big boy come home last week, and big boy was very happy to see Ozzy. He didn't get. Everybody's like, "Are you excited for Cole to come home? Is Cole excited to come home?" I'm like, he wants to see the dog. He doesn't really care about the rest of us. He wants to see the dog. And then I sent him a picture Sunday afternoon after he'd already left. And he writes back, I miss him so much. Not I miss y'all. I miss you. I miss him so much. Thanks. We miss you too. Uh-huh. All right. So energy and work. So what do we call the ability to do work, Miss Bay? That is energy, which makes sense because we use this colloquially the same way, right? Like I have no energy today. You can't do work. If you don't have energy, you can't do work. So that's a definition that is the same conversationally as it is scientifically. So energy and its forms. So today in lab, we did some gravitational potential energy, some elastic potential energy, and we did some kinetic energy as well. So energy has two main forms you can subdivide it into. All right, Colin, what you got? And kinetic and potential is right. All right, so let's look here. You got kinetic, and it's further subdivided into mechanical, thermal, sound, electric, and radiant electromagnetic. And then the other kind is, you said potential, right? And potential is, guys, I clicked you. There you go. Potential is further subdivided into gravitational, chemical, nuclear, and elastic. All right, so let's have a closer look. So what kind of energy is energy of motion, Liam? Kinetic is energy of motion. All right, so, yep, Newton's cradle, sort of. It's a weirdly tangled one, but it's there. So, AI, man. So yes, kinetic energy of any moving object depends upon its mass and speed, which makes sense if you think about a telephone pole versus a bus versus a Mini Cooper. Now, what if the bus is doing a half a mile an hour and it's just barely rolling versus the Mini Cooper doing 80 miles an hour, if they're even capable of that? Assume they are, but they're
Go ahead and
there you go. Yeah, so obviously, even though the Mini Cooper's got less mass, it has more speed at that point. And if you flip-flop them the other way and you have a bus and it's going like 80 miles an hour, you're going to have a lot of speed and a lot of mass. So that's a ton of energy, right? All right, so like we said, we have our major forms of kinetic energy: mechanical, thermal, sound, elastic, and radiant electromagnetic. So look at them more closely, but you've got to get your Mentimeter ready. I'll give you a second. Sure, I stole some of your goldfish. Thanks. They're so good. Okay. It's okay. You can still guess. You can't get it?
There's a glare. Oh, there we go.
You got
Not
it?
there yet.
Okay.
There we go. There was a glare.
I'll give you all a second to get it.
Ozzy? No, I don't have any
Spoiled
more for
dog.
me. No more. He's just looking around.
Hey.
Oh, can't open page.
All right.
Oh, he's looking at my bag. I have
Oh,
banana bread.
yeah, well, there were some random kibble bits that went that direction at some point. Go lay down. Go. Go on. All right, are we good?
No, wait, I'm not connected
Here.
yet.
Oh, here. I'll give Jordan a second to get logged on. So what we're gonna do here is, right down there is the password and everything. So I'm gonna give you all a second to get yourselves logged on. And then what we're gonna do here is we're gonna talk about a form of energy, and then there's a little video, and you're gonna guess what's gonna happen in the video. Yes.
What's the height of the ceiling?
I do not know. It's a great question. Not a clue.
I'm gonna take a picture.
All right, so forms of
Am I-
kinetic
am
energy.
I-
Oh, hang on. Give him one more second.
You are 20?
Hmm? Feet? Probably, but you need to make that in the meters, so. Yeah, really. Did you get it?
There we go.
All right, okay, so what kind of energy do we associate with motion and position, Caitlin?
Mechanical.
That is right. Okay, so mechanical energy is what we associate with motion and position. So anything that is moving or that is contacting something else, that is mechanical. All right, so what do we think is going to happen here? All right, our options are hit the pavement, hit the tree, or hit the books.
I can't see it from here. I can't see. What's it holding?
I can't tell you what he's holding. I'm gonna mess it up.
Where are the books?
I gotta go.
All right, so mechanical energy, energy in motion.
There are various types of energy.
No,
including
Alexa,
conflict.
stop.
But I gotta go get the book. Aww.
All right, go. He hit the books, clearly. Mechanical energy, swung the bat, he smacked the book. Book fell down. Book, go boom. There you go. One more time. Yeah. All right, so what kind of energy are we talking about here, do we think, Ridley? Thermal, okay. Why is thermal energy a type of kinetic energy? If energy in motion, Yusuf?
Because of the total potential and kinetic.
What?
It's the total potential and kinetic.
Right, so, yeah, James, you want to add to that? That's where we're going. Okay, yes. So, do you remember the definition of temperature? Do you remember, Bailey?
How much molecules move around.
Yeah. It's the total. Yeah, it's a measure of the total amount of motion you've got going for particles, right? So within a substance or an object. So obviously, when you heat things up, we know that makes the particles move faster, spread out, move around more, right? So that's why thermal energy is a type of kinetic energy, even though you might not think of it that way because we don't see the motion, but the motion's there on a microscopic level. Okay, so what's going to happen here? Hot steering wheel, hot outside, or a hot buckle? It didn't go? Oh, hang on. Is it going to make me... Hold on. Is it going to be up? Hold on. It should be going, but if it doesn't, maybe I can make it. No, don't do that. All right, let's see. There we go.
There we go.
All right, you got it now? Hot buckle.
No one did hot outside.
Hot outside or hot steering wheel?
It's basically, it depends where you are.
Because
And it doesn't have to be hot outside to be a hot steering wheel or buckle. I learned the hard way. Why does it say vine on all of these? Because
I
vine-
intentionally picked short ones when they're vines.
It's before TikTok.
Way back in the day, man.
Yeah, it's dead now.
The original TikTok. Yeah, before
Better
China created TikTok and spied on us all. All right. So here's what happens here. Let's see. There we go. So yeah. Hot buckle. Clearly a hot buckle. One more. Burned himself. Yeah, you don't want to drown yourself. Alrighty, so what kind of energy? This is kinetic too. Has to do with vibrations transferred by waves. PJ. She got it.
Electromagnetic.
Not electromagnetic. One more time. Yeah. You want to guess, Liam? You're about to die over there. Nope, not radiant. Oh, all right, Jordan.
Chemical energy.
Y'all are killing me. Oh my God, Xander. No, Asher. Sound. Okay. So sound is, it says it right there. So sound is kinetic because those sound waves are moving, right? So we don't think about sound as energy, but it is, and it has to do with moving.
What's that instrument on the right?
It's some special kind of a rat instrument that is only for rats. I have absolutely no idea what that is. That's AI going, I'll make something. Watch me. Yeah, sort of. So what's going to happen here? Your options are Italians blowing things up, Russians with jackhammers, or Canadians with musical instruments. What do we think?
Italians. Those named Italians.
Why not?
Alex would like them.
There you go.
I Alex would like anybody blowing
It's
inside.
like blowing up.
Barely. They have different reasons.
Woo. Somebody's hoping for Canadians with musical instruments. All right. That would be Italians blowing things up.
Oh, yeah.
So you can hear that wave echo through the whole tunnel. Yep. So listen to it again. You can hear it echo. Mm-hmm.
Really happy.
Anybody ever been in the mine in Dahlonega and had them turn on that jackhammer thing in there? Oh my goodness. It's crazy loud. So we have another form of kinetic energy, and this one's associated with electrical charges, Emily. Yeah, that's a good one there. Okay, so why is that kinetic? No, it's on a table. He's on a table. He's small. So why is it kinetic, Yusuf?
Yeah, so that would be moving.
Electrical particles move. Yeah, which particles are moving? What's actually moving? You know? Yeah, electrons are actually moving. So when you've got electrical energy, you're dealing with electrical charges, and that the motion there comes down to the actual electrons shifting. Okay. So yeah.
His glasses are actually hovering in midair. He's not even like.
Oh,
Sounding good. You just can't because his little whiskers are here.
No, you threw it up.
Hold it now. So, okay, now what's gonna happen here? Brim touches wire, lightning strikes Brim, or Brim plays music. What do we think?
Like it's
Brim touches wire, lightning strikes Brim. Brim plays music. That'd be cool.
I mean, he's singing.
Oh, let me just say, it was a challenge to find something with electrical energy that was funny, but not like really sad or like where you go, oh gosh. I mean, I still say, oh gosh, but yeah. All right. So what happens? You touch the wire with the metal broom. Now, I really love, though, he's in a great mood. He is singing. He is having the time of his life up there. And then zap. All right. Who's been shocked before? Yep.
It hurts.
Yep. Okay. What shocked you? Like when you plug something in, you got zapped? Did you get?
Going down those slides in the winter.
Oh, static shock. Mm-hmm. Yep. Yeah, the tube slides. Who's ever, so aside from static, who's ever gotten zapped? But you got, what happened?
I tried to get a socket out of the plug.
Mm-hmm.
Plug out of the socket, and I touched the metal.
Ah,
I did that twice on two occasions.
it's terrible, isn't it? It is awful. How about you?
First time I ever changed the light bulb. I
Oh.
was like 10. I was like, what's this?
Oh no. Yeah. There was a Christmas tree topper that I had when I was a kid, and it was shaped like a star. And there used to be the blinker bulbs, like if it was gonna blink, you had to let it warm up and then it would blink. And I didn't want to wait for it to warm up, so I was trying to do like a show for my mom and my mom, and I'm like plugging it in and out, plugging it in and out, and I'm like, oh, it got me really good. That, and one time I was standing outside right after I got to Georgia. Jason was living in an apartment complex at the time, and I was over there, and I thought I heard tornado sirens, which I'd never really heard before because we didn't really have those where I grew up. So I stepped outside to listen, and I was leaning with my hand on the gutter, and there was lightning everywhere, and it was I could see it, but it wasn't like right where I was, and it still traveled enough that I could feel the buzz like in my hand, and I was like, no, not good. And then my best friend was one of those kids who like to stick 9-volt batteries on her tongue, which if you've never done that, it's an interesting sensation. It passes a little 9-volt current through your tongue, which isn't terrible, but it feels pretty gross. Yeah. But That's how old school dudes like my dad check to see if the battery still has charge before they use it. I stick it on. Oh, wow, this one's good. Yeah, that's how you find out. Uh-huh. Oh yeah, but yeah, especially if you have braces or fillings, and chewing on tinfoil is a gross feeling too. Yeah. All right. So what's next? Let's see. Yeah. Mm-hmm.
Yeah.
Oh no, we saw you. Ooh, ooh. Okay. So, what kinetic energy travels through space? Emily? Electromagnetic or radiant energy. So yeah, so where's that coming from?
Outer space.
Yeah.
From the sun.
From the sun. There we go. Yeah, so she's chilling on the beach in her bikini. She is thinking she is awesome, right?
I never thought that's so beautiful.
Yeah, I didn't know they needed clothes either, but she's looking pretty chill there. So does all electromagnetic radiation come from the sun? No. Give me an example of something that's different. What you got, Lucas?
A light bulb?
Light bulb. Okay. Yeah. James? An electromagnet. That's a very good one. There you go. Drew?
Your magnetic field.
Earth's magnetic field. Asher was going to do that one. He's like, man. All right. How about you?
Another star?
Another star. Yeah. How about radio?
Yeah.
Microwave? These are all things we create. Uh-huh. Gravity? Okay. So yeah. So we have electromagnetic radiation. We have a visible spectrum, right? That's all the light that we see. But there's plenty of electromagnetic spectrum that's not visible to us, that's around us all the time, right? Like we've got gamma and infrared and ultraviolet and all these things that are around us all the time. We are swimming in electromagnetic radiation constantly. Like, and it's not necessarily bad, because we'd all be like, you'd have 4 heads or something and 2 tails if that were the case. But no, it's everywhere. It's around us all the time. So what's gonna happen here? Okay. So does he avoid a sunburn? Is he proud of his tan, or is he just a dork?
Door. Who's both a door?
This one was an absolute must for me when putting electromagnetic radiation together. Yeah, it does say dork in the title.
The
It's
title.
a shame that pops up. So this is from Police Academy 5, and this is a classic. Real good. Real good. He's the captain, by the way.
Oh, I think they're gone.
Mm-hmm. He's sound asleep in the sun.
What's happening, George? George?
People in this speech are very rude and us.
Great movie. If you've never seen it, really good one. But yeah, he's dork. They put dork on him in the sun. Yes. So obviously, because there is energy involved with electromagnetic rays from the sun and light energy, in particular ultraviolet, which we don't see, right? That's not visible spectrum. That's what's at the very, very far end. Like, but that's what causes burn, right? Because it's energy on your skin. No, we saw you. All right. So kinetic energy. There is a formula if you're going to calculate kinetic energy. So it looks like so. Now we were talking about mass and speed, or mass and velocity, at the very beginning when we define kinetic energy, that it's affected by the mass and velocity of whatever object is in motion. So somebody come up with an example for me of an object with large mass, but very low velocity coming in contact with something else. What's a good example? James. But the tree's not moving, is it? Or it is, but not. Yeah, it is yeah. So how about something with a lot of mass but low velocity that could bump the tree or hit the tree? Yeah. Oh, no, got a different one? Go ahead. What's your different one? Not sure. The what? The moon. Oh, I didn't hear you. Okay, the moon. Yeah, there you go. All right. So an elephant. Okay, so I want you to think about everything you just named and then think back to when we very, very first talked about motion. What was necessary to describe motion?
The direction.
Direction. Mm-hmm.
Speed of the.
That's one. What else? Drew. Frame of reference. There you go. Point of reference or frame of reference. So from our point of reference, the moon's moving pretty slow. And then from our point of reference, the tree's not even moving. Right. But they are moving. Yeah. 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 The wind is moving them around. There's that. Yeah. So remember that your point of reference is going to impact that velocity there. So like I said earlier, if you have a tiny little Mini Cooper and you're driving it at 0.5 miles an hour and you're bumping it into a telephone pole, you're probably not going to get a lot of damage because there's not going to be a lot of energy involved in that collision. But if it's like week before last, did anybody see on the news how I-75 got shut down week before last? I mean, they closed it for hours. There were 3, they were described as semis/moving trucks. So I assume full of furniture, fun, and 7 passenger vehicles that were involved in a massive crash at Windy Hill in 75, shut down the interstate for hours. Think about the amount of energy involved in a semi hauling furniture going 65 miles an hour.
Yikes.
Do you want to be in the passenger vehicle nearby? No, you don't.
That's why you don't brake check semis.
That's a good point. Yeah, let's not brake check semis
Or
ever.
don't check anyone.
Yeah, true. All right, so
Birds.
you might want to write this down. This little formula. So if you can't see it in the back, it's kinetic energy equals 1/2 mv squared, mass velocity.
Oh, what did I just?
All right, and hopefully we have some paper. Let's give it a shot. Get you some paper. You don't have paper. Yeah, slide around if you want. Yep. Okay. There you go. So what are we solving for, first of all? What are we trying to find?
Acceleration.
Well, we know what its kinetic energy is. So how fast is a ball rolling if it contains 98 joules of kinetic energy and has a mass of 4 kilograms? What are we trying to find?
Velocity.
Velocity, there you go. How fast? There's your clue. Now give everybody a minute. Don't put your hands up. You know the rules. Liam's like, no math, please, no math.
Oh, my back.
Oh no, sorry.
I practiced on some.
Oh no, was it rough? Oh man. Does anybody want to volunteer?
Just give it.
Okay, give y'all just a minute more and I'll let you go, PJ, but I'll give everybody a second. Okay.
7.
Let's see, does it equal 7? All right, 7 is right. So how'd you get it? So your speed of the ball is given, the speed of the ball at the given mass and kinetic energy is 7 meters per second. So how did we figure that out? We knew what the joules were and we knew what the kilogram were. So we plugged them in, ding, ding. So we started like so. You had to take the square root, right? Because we started with something squared See, it's v squared, your velocity squared. So in order to get your velocity itself, you have to unsquare it. So you're taking a square root, right? So when we plug in our numbers, works out like so, and we get 7. Good job, PJ. That was good. That's a good one. All righty. So what kind of energy is stored as a result of position or shape? Xander.
Elastic.
Elastic. All right. Well, potential energy. Elastic is a form. We did that today. All right. So potential energy is energy that's stored as a result of position or shape. And we have our major forms of this, which are gravitational, chemical, nuclear, and elastic. Chemical and nuclear are both going to be stuff that you're dealing with on a molecular or atomic level. Okay. So these are the ones that you don't necessarily see. You can really like see with your eyes, gravitational and elastic. So, all right. Jingle bells over there. All right. So what here do I want? Potential energy that depends on an object's height. All right, Caitlin.
Gravitational.
That is gravitational. All right. Who's been skydiving? Anybody been? Anybody been to, nobody's been skydiving outdoors at your age, but anybody been indoor? Yep. Okay, we just did it over break. It was fun. So what kind of things did you have to do in order to be able to successfully fly, Colin? Yep, put you in a big old suit. Yep. How about you, James? Oh yeah. James is showing spread out. All right, yeah. Caitlin, what else? Were you gonna add anything else? Yeah, there's a person there to help you. So we went to iFly. We actually, Drew's grandparents gave it to him as a gift last Christmas, and we hadn't been. So we just finally went when Cole was home right before Thanksgiving. And it was a very, very interesting experience. So it's a high-speed wind tunnel, right? And you get in it, and the wind is blowing up, and you just sort of like, whoop, you kind of dive in, right? And there's a guy there, holds on to you. But he did some very interesting things at the end. He did like a demo for us. And I noticed that he was making himself go up and down, up and down. And there was a guy who was definitely controlling like the velocity of the wind, the upward wind. But when he wanted to go up, he shaped himself like this, and he went all the way to the top. But when he wanted to come down, he shaped himself like that, and he came back down. Why? What is he doing? What's it?
When he curved, the wind got caught and pushed him up.
Yeah, yeah. When he hollowed, yeah. What? No. Mm-hmm.
Why is it jumping from a hot air balloon?
People do that.
Also, yeah.
Yep.
It's extremely long.
So yeah.
That's
So,
helpful.
It's your angle. So anyway, so yeah, so when you hollow like that, you're creating more drag, right? More air resistance, more drag, and due to shape. So when you're talking about gravitational potential energy, you have to consider the mass of the object, but also the shape of the object when it comes to how it interacts with the fluid it's moving through, right? This is the same thing like why are cars all angled as opposed to big flat fronted things like semis and stuff? Because you get better, you cut through the air better, right? So that same concept when you're heading downward. All right. So now let's say, so as we said, mass and height. Think about this too, like dropping a 1 kilogram mass and a 10 kilogram mass. They're both going to fall, but one of them is going to have more energy when it hits the ground, right? So what's going to happen here? Here are your choices. Human pinball, humans versus gravity, or near misses. What are we going to say? Human pinball. So thank goodness for gravity. Good thing we have it, but sometimes it's not our friend, especially if we're not graceful like these people. This is humans versus gravity, clearly. Yep. Little humans versus gravity. So yes, gravitational potential energy. One more in case you missed any of it. Don't know why you do that. Or this. That has to hurt for sure. Yes, fun times, gravity. So here's your formula for gravitational potential energy. And you did this today, kind of, sort of, a little bit. You did more elastic, but I think there was some, wasn't there a gravitational one? No, it was just elastic. Anyway, So gravitational potential energy is the energy stored in an object due to its position. And these are the things you need to know. You need to know mass, gravitational field strength, height, and gravitational potential energy. That's you can find that if you have these other things. What is the gravitational field strength going to be? Do what? Yeah, but what is it? Like, what are we looking for there? What do we use if we're trying to solve something? What do we use? If you're here on planet Earth. PJ had it in lab.
Oh. 9.8?
Yeah. You're looking for your constant. There you go. So here we go. That's what you're gonna want. So 9.8 you can use is 10. Why did she say 9.8? What is 9.8 meters per second squared? What is it? It's the what, Drew? Yeah, it's a gravitational constant on Earth, or G, right? There it is, a lowercase g. So that's what you're using, gravitational constant. So in this case, Roger Federer's tennis ball has a mass of 0.3 kilograms. If he holds the ball above the ground at a height of 2 meters to serve, what is the gravitational potential energy? So for simplicity, you can round G to the nearest whole number, which is 10. Yeah. Caret. Always the answer. Yeah. Give y'all a minute. All right. Juice. Okay, Colin, what do you think? 5.8. Anybody have anything different? What'd you get?
I rounded to 10 to 6.
You rounded to 10, so 6. What'd you get?
6.
6. Okay. Yep. So if you're rounding, that's where you're headed, right? If you're not rounding, you're getting 5.8. So there you go. Very good. Very good. 6 joules in its energy. So we're doing it that way. All right. Elastic potential energy. So this is really the heart of your lab, right? What? He's cute. He's working out. Respect. He's wearing, it's a fuzzy sweatsuit,
It looks so cozy right now with the temperature.
right? He's working hard, man. He's got a sweatband on. He's for real. So what is this one, Milo? Elastic potential energy, right? Okay, this is when an object is stretched or compressed. This is involved in earthquakes, right? Rocks are not all that elastic, most of them. They're rather brittle, they're rather rigid, they're not so malleable, and they'll only stretch but so far before they slide really fast and hard, right? And this is also it's also important to keep this in mind when you're building tall structures. Like, look at the trees. You're watching the trees, they bend when the wind blows. Thank goodness, because if they didn't, they'd all snap off, and that would be terrible. You ever been in a tall building and felt it sway? Yeah, there has to be some elasticity in the structure in order for it to not be damaged by wind and whatnot. So this is my favorite of all of them. What is going to happen here? So someone gets a wedgie. The wall is bouncy, or chicken laughter.
I'm gonna win the chicken laughter.
Reggie and laughter.
So this is a game I want to play at my next gathering. I don't even care who I'm gathered with. I want to play it. It's good fun. So they have, before we begin, they have rubber bands around their lower legs here. This is smart.
Yeah, I've seen some YouTube too.
Oh, they have harmonicas in their mouth.
No, they have rubber chickens in their mouths. They're trying not to laugh. They're rubber chickens.
They're trying to what?
He's good.
I think it's more like a team color thing in this case.
Mm-hmm. The best. I've let you all watch each one of them twice, so I'll let you have that one more time because it's way too good. It's way too good. And you can see the further back they stretch it, the more energy it's got. That's great. This guy's rubbing his leg in the back, like, take on. I'm laughing with the chickens in the road. This is too funny. He's good. I'm impressed with that guy. This guy, not so much. Too funny. I think he's laughing. That's a good one. Good. It's laughing. So
Oh,
it's probably laughing through tears. Yes. So elastic potential energy is energy that's stored in an object as a result of deformation of an elastic object. So for example, stretching a spring. Now, when you're doing these equations, one thing that really helps is if you have a spring constant, and that will be given to you based on the spring. They're not all the same. Like springs, some springs are, you know, obviously less stretchy, others are like real stretchy. So the spring constant, it has to be something that you know if you're going to calculate this. So how about we do this? Joe pulls a spring with a spring constant of K equals 100 newtons per meter, stretching it from its rest length of 0.1 meter to 0.2 meters. What is the elastic potential energy stored in the spring? Okay, so your extension will be from rest to where he stretched it. So you need to find a difference there between the 0.1 and the 0.2. Well, give everybody a minute. Don't put hands up yet. All right, anybody have it? Okay, Xander. Oh, Lucas, I'm sorry. I looked right at you. Both were in half today. 50, he says. Anybody have anything different? PJ? 0.5. What do you have? Whoa, okay. Okay, so we got some different answers. So let's have a look. So our extension is 0.1, right? Because it's a difference. So this is what we're going to do. 1/2 KE squared. And that is 100 here. That's our spring constant, right? And this is our extension. So when we do that, this is what happens when you square it. And we have a 0.5. Very good. Ah. Do what? 1 divided by 2? Yeah, 1/2. Yeah. That's 1/2. So what kind of energy is stored in chemical bonds? All right, Caitlin. Chemical energy. Now, we tend to think of batteries as a good example of chemical energy, right? They produce electrical energy when you get them hooked up to the right components, but just sitting there by itself, the battery does absolutely zilch, right? It's potential chemical energy. So what's going to happen here?
potato.
Potatoes run a fan, potatoes make a light, or potatoes get mashed.
Potatoes get mashed.
Yes.
Ooh, y'all are still hungry. You just had Thanksgiving and you're still hungry. Y'all are going for mashed.
Stupid answer.
That's exactly what we do. What else do you do?
Only 3 of you answered? Oh, here we go. Potatoes make light. All righty, let's see. What do we get? That helps. That was an expensive copper plate he just whacked up. They're not cheap. Cool, right? They should make all flashlights with potato batteries. That would be a thing.
It would have been awesome if they got mashed at the end.
That would be cool. For real. Anybody ever done that? Anybody ever done a potato battery?
Yeah.
Yep, done 'em.
Lemon.
So next semester, oh, lemons, yeah. Next semester, we're gonna do all kinds of fun stuff with,
Yeah.
you're doing, oh, green apples. We're gonna do all kinds of fun stuff with electrical stuff. We're even gonna make like a telephone, like a very primitive kind of telephone. Pretty cool. Yep. All right, so next one, move. So what kind of energy do we store in nuclei? Who hasn't answered me yet? Oh my goodness. I'm trying to look for somebody who hasn't answered. Chloe. Very good. We don't say nuclear, do we? No, I kick you out. You say nuclear. Nuclear. What is happening in a nuclear reaction where we're getting nuclear energy? What's going on?
A lot of times explosions.
A lot of tiny explosions. Okay. What?
The particles collide.
Okay. James, do you know? Were you gonna add something?
The nucleus is,
Nucleus is moving. What are you gonna say?
they're pulling apart atoms.
Pulling apart atoms. Yep. What are we gonna add?
Nothing nice.
Split the atoms, you get big boom.
Yeah, you split atoms, you get big boom. Okay, so something we'll talk about a lot next year in chemistry is that when chemical bonds form versus when chemical bonds break. So think about it for a minute. Which do you think is going to require energy to be put in, breaking or forming? And which do you think is going to have energy coming out, breaking or forming? You know, remember? Yeah.
Breaking test its energy to go splitting apart.
Say it again. Yeah.
Forget which way. Breaking
Yeah.
is when you break them apart, takes energy, and
Mhm.
put them together.
Uses energy, right? So if you're gonna bond things together, it's gonna require energy. So if you're forming a bond, it's gonna require energy, and if you're breaking a bond, it releases energy. So anybody ever used one of those little ice packs that you break and then it suddenly gets cold? Yeah. Back when I worked at cottage school, man, kids would come in with like nothing wrong just because they wanted one of those. Oh, my toe hurts. Can I get a nice? Because they were fun. I don't know. So yeah. So what's happening? Why is it getting cold? What's going on? It's chemical reaction, but what do you think?
There's a little pouch inside
Mhm.
the break.
Yeah.
And it spills out into everything else. You shake it up and make it makes cold.
Right. So what kind of a reaction do you suppose it is? Do you think you breaking bonds or forming bonds if it's getting cold? Yeah, you're forming them. Yeah, if it's cold, it's because you're forming bonds. So it's taking energy from outside. And now how about the ones you use when you go skiing and you smash them and put them in your gloves and they keep your gloves warm, the hand warmer ones. You know those, the hand warmer kind? So it's the opposite. In that case, you're breaking the bond and it's releasing energy. So it's getting nice and warm. All right, so let's look at this one. What's going to happen here?
Oh, no.
Homer gets it wrong.
Homer.
Homer gets it right, or Homer gets nuked.
No, he gets it wrong.
He gets nuked.
You've
I've never seen this show. I don't want to see Homer get nuked.
never seen this
No, I'm not.
Oh,
How
no.
dare you?
episode.
Your dad says what? That's great.
What did he say?
That's great.
That is true. Oh, you can call this.
Down.
It's this.
Exactly.
Hey, I didn't let you watch SpongeBob because I didn't like him. Well, there you go. I just didn't like him. All right, so Homer gets it wrong, or Homer gets it right. All right. Remember what I said about that word.
Now, Simpson, because of your many years as a nuclear technician, we're putting you on a nuclear sub.
Nuclear. It's pronounced nuclear. Nuclear.
Did he get it right or wrong? You got it wrong, yeah. Nuclear. And he's very convinced that that's what it is. He's wrong.
Simpson.
No. All right.
No, Simpson.
Conservation, energy conversion and conservation. Okay. So what's the law of conservation of energy? What's it state? James. Yep. What other laws in science do we have that are very similar? Can we think of one? Lucas, Xander, y'all are today mid hats. Crazy.
Conservation of mass.
Conservation of mass. That's another one. What's another one?
Conservation of matter.
Conservation of matter. Yeah, mass and matter are the big ones. Do you have another one?
Momentum.
Momentum. There you go. Mass, matter, momentum. Do you have a different one back there, Lucas?
No, it's just that he's drinking something while on that, so he gets choked on it.
You're not gonna choke. He is an expert Peloton rat, and he's drinking his protein shake. Gosh darn it.
Why is it so bad?
Because he needs to be on his Peloton every day. He's on there for a reason,
You
man.
just started yesterday.
Yep. So energy cannot be created or destroyed. It only changes form. Same thing you can say very similarly about jingles, about mass and matter and momentum, right? So energy and mass. Einstein's most famous equation, equals mc squared, right? Says that energy and mass are what? Look at it mathematically, Bailey. There you go. They're proportional and can be converted into each other. If you've got energy and mass, think back to what was the other one that we had that was a lot like this, that was proportional? We talked about one of the product. How about F equals ma? Is force proportional to mass?
Yes.
Is force proportional to acceleration? Is mass proportional to acceleration?
No.
No. So is energy proportional to mass here?
Yes.
How about, is energy proportional to the speed of light?
Yes.
Yes. Is mass proportional to the speed of light?
No.
No, right. Proportional, you have to have that little equal mark in between,
Yes.
right?
And then to make them proportional, you have to change it.
Yeah, you'd have to flip it around, right? So energy can be converted from one form to another. So what do we call it when it changes form? Caitlin?
Energy conversion.
Conversion. All right. So this is going to be like at the very heart of your Rube Goldberg builds at the end of the year, is energy conversion. You're going to have to tell me what kind of conversion you've got going on. Like, oh, we have potential and now it's kinetic. Those of you that hung around last time and watched some of the videos from last go around 4 years ago. Although even Sky sticking her foot in the frame and kicking it every time it stopped moving. Great fun, right? But that's because you need to show the different conversions from one point to another. All right, so let's think here. So there's some kind of energy in this clock, and it's going to get converted into sound. This is an old school clock. What do you think, Colin? Time. What kind of energy is going to produce sound here? Jordan?
Elastic?
Elastic is part of the equation for sure. Absolutely. What do you think, Liam?
Mechanical.
Mechanical. Okay, so we have mechanical at the end. Okay, that's our last step. You see this little hammer right here? These old school alarm clocks, that hammer goes ding, 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 right? It goes back and forth. But what were you gonna say, James? Yeah, and then it's kinetic. Yep. So it's a form of kinetic. It's mechanical kinetic. And were you gonna something else? Sound is what comes, right? So, but in order to make the clock work at all, you have to wind it. Okay, so these old clocks had a spring. You wound the spring and the spring slowly uncoiled, and as it did, it's what caused the hands to go around and it would release the hammer when it was time for the alarm to go off. So that's how the old clocks work. If anybody ever used one of these before, I had one. It was cool. They're very loud. Like they will wake you up. They are good and loud.
There's no snooze button.
Nope, there is no snooze button. It's just good and loud. All right, so how about this one? So this dude's eating some breakfast here. He's got toast and I don't know, butter, orange juice, coffee. He's got everything out.
Yeah.
So some kind of energy here is going to be converted into other kinds of energy throughout the day. So Colin, what do you think? Chemical? Yeah. What's it going to get converted into? Asher? Not clear. Boom.
Nuclear.
Yeah.
Radiant.
Radiant? In a way. Yeah.
Oh, kinetic and potential.
Kinetic and potential. Yeah. You gonna add anything else?
Carrot energy.
Carrot energy. So we got a couple things going on. What?
Chemical energy can be converted into mechanical energy.
Yeah. So there is all the above. There's a lot going on here. So basically you got your chemical energy of your breakfast, right? And you're going to convert it into mechanical, kinetic, but also thermal. This is why you're warm, right? We have endoderms, endotherms and ectotherms. Which are we? Do we know? Who remembers? You, James? Yeah, we're endotherms, right? We produce energy as part of our chemical reaction for aerobic respiration, which is respiration on the cellular level, which is the opposite of photosynthesis, right? So we produce heat, thermal energy as a byproduct of that. So without that, we'd be in some pretty bad shape. We're meant to run at about 98.6 Fahrenheit, right? All right, how about here? So we got some kind of energy conversion. What's going on? What do we think? Yusuf?
The thermal energy.
There's thermal involved. What are we starting with, Jordan?
Kinetic.
We got kinetic involved. Yep. What are we starting with? Where's we starting with? Okay. Go ahead, Lucas. Shaking your hand everywhere. Electrical. Okay, good. All right. So, but here's the big question. Where's that energy coming from? Do we even know?
It depends on the plant.
Depends on where you get your energy from, where your electrical energy is sourced from. Where is the electrical energy sourced from here primarily?
It's the dam.
Yep,
It's
it's hydroelectric
yeah.
primarily. Yep, we have primarily hydroelectric, but there are places where it's solar, there are places where it's coal, right? And those are all, so you got all this energy conversion. And if you can trace it way back, so gravitational is the one that's a little different. But if you trace back, let's say you live in a place that gets its energy from coal, and you're blow drying your hair. Okay, so you've got kinetic energy and thermal energy working to dry your hair, right? Which is electrical energy, which came from the burning of coal, which is what kind of energy would that be?
Nuclear.
Chemical. Yep, it's chemical potential till you burn it. Yep, but where'd that come from? Where'd the coal come from?
The ground.
Animals.
Dead dinosaurs.
Biomass. Yeah, dead, primarily plants, swampy stuff. And where'd that energy come from?
The sun.
Yeah, so you can trace most, unless except for the gravitational stuff, you can trace most of it back to the sun, which is pretty cool, actually. Yeah,
How is the hair dryer floating?
it's magic.
Yeah.
It's magic. He's a magic rat.
AI.
Magic rat. Okay, we're going to assume this is an incandescent bulb, not an LED like everybody has these days. So what kind of energy do we have here? And so what kind of energy are in the batteries and what's it being converted into? Okay, Caitlin.
Chemical,
Got that one.
electromagnetic.
Yeah. Light energy is one. Yep. And what else? What else, Xander?
Thermal energy.
Thermal would be the other one. Yeah. So light bulbs that are not LED bulbs, incandescent bulbs, they get hot, right? I mean, they get for real hot. You ever touched one? Yeesh. Yeah. So flashlights weren't ever too bad because there was a gap between the bulb and the lens, right? But still gets pretty hot. So LEDs don't get so hot.
Have you ever touched the spatula?
No, I like my fingers. Have you? Do you not like your fingers?
No.
Oh, that glowing thing wasn't a clue that it was on fire. Oh, okay. Well, then maybe an excuse at 5, I guess. All right, so here we've got gravitational potential energy of this water balloon, and it's going to get converted into what kind of energy as it falls? Yes, kinetic, because it's in motion. Yep, if it's in motion, it's kinetic energy. And that poor little guy on the bottom doesn't know it's about to hit him. Sorry, dude.
Or he doesn't actually accept his fate.
Yeah, maybe he wants it.
It's a moment that this moment you realize.
Yes, it is. So let's talk about energy resources then. So we've been talking about all the different kinds of energy. Where do we get our energy? So we talked a little bit. So we have 2 major categories of energy resources. We have some that exist in limited quantities and they cannot be replaced once used except over millions of years. And we call these, Ridley, they call these non-renewable is right. Okay. Technically, some of these that are non-renewable, really, really renewable except millions of years, right? That's what we say, millions of years. So examples would be things like oil, natural gas, coal, and uranium. So think about this now. We talk all the time about sources of clean energy. Now, we lump nuclear in very often with clean energy sources, but it's non-renewable. The reason we aren't so worried about it is because you don't need a lot of uranium for a nuclear reaction, for nuclear power production. You really don't need a whole lot. A tiny bit goes a long way. Yes.
Isn't solar power renewable energy?
Yes, it is. So this guy just happens to be working on the solar farm. He's an engineer. I mean, look at his tiny too short shirt. It's cute. He's dressed like Dora the Explorer. His shirt isn't long enough. Yeah.
Depending on the gain weight, uranium has like 40,000 calories.
My word. Okay, there's that.
Well, you want to get superpowered.
I saw a meme just yesterday and it had Marie Curie in it. And it was something about, I don't know, it was something about glowing was the meme. And it was funny how many people were like, haha, that's just innocent fun. And other people were like, she died for you. She died in the name of science, which is true, she did. So anyway, that was radium primarily still. All right, so what energy resource with this? We can replace it in a relatively short period of time. What are these? All right, PJ? These are renewable. All right. So we consider the following to be lumped in. So what's this one? This is where you get water flowing. Yes, Liam.
Hydroelectric.
There's our hydroelectric. So this is what we have, right? We got hydroelectric primarily right here where we live. But there's lots of other sources. Most of the state, I think, when we did it in earth science, didn't we find out most of the state was hydroelectric?
So
I think most of Georgia is, yeah. And that's not always been the case. So good thing that it is. So which form of energy is this? It's renewable, but we're talking about energy and energy transfer. What kind of energy is this? Okay, Yusuf?
kinetic.
It's kinetic, yeah, but it is specifically coming from gravitational potential. In order to have a dam work, you have to have, the water has to flow, right? So it means it has to be going down. So, yep, so you have gravitational potential energy at work, and it produces kinetic energy because it turns the turbines, which is then converted into electric energy, which comes into your house and you make it into whatever you're gonna make it into. All right, the sunlight is what, Drew?
Solar.
Yeah, that's an easy one. And what form of energy would solar be then?
Thermal.
Thermal is part of it. Yep. What else?
Electromagnetic.
Electromagnetic. That's our big one. All right. So yes, electromagnetic energy or light energy, right? Coming from the sun. All right. And how about, what's this one going to be? Earth's thermal energy from Earth's surface. Ridley. Geothermal. Very good. And what do you think geothermal is as a type of energy? Colin. Chemical? It could be in some places, but yeah, it's what? Why does that just say that? That should say, that's not right. That should say that it's thermal coming from Earth, but yes, but where, why, what's the heat coming from? The mantle, and what's causing the heat in the mantle? Bailey? The core, yeah, pressure, yeah. Yeah, exactly. All right, and then we have this little farmer guy. So what do we call chemical energy that's stored in living things? Okay, Emily. Biomass, right. And then what type of energy would biomass be? Jordan. Yeah, potential chemical until it's used. Exactly. So that ear of corn right there is packed full of chemical potential energy. If it can power you, it can power cars, right? You ever seen the cars that run on biofuel? They're more like experimental vehicles because obviously they can't mass produce it. It's not efficient enough. Yep, but it's an interesting experiment. And Back to the Future, was it Back to the Future 3 with the Mr. Fusion, with they shoved the food into it? That was entertaining. Yes,
That is the smallest ear of corn I've ever seen in my entire
he's
life.
very tiny. Yeah, he's a big rat. He's big. All right, how about this one? Hydrogen and oxygen. All right. Ridley, I'll go with you again. Yes, fuel cells, hydrogen fuel cells. Now they have made these in cars too. And these are kind of cool. Actually, I had a friend in college who worked on it. He was working on an oxygen type of fuel cell, more oxygen focused. But because they were at a research institution, they actually got special paint from DuPont. Now we see this paint everywhere. You know, they're like the Mistachrome cars where you, as you pass them, they change color as you go. At the time, that was a real cutting edge in the early 90s, but it's like a 5-sided crystal, the paint. So it had 5 different, it reflected 5 different wavelengths. So depending on how you looked, it changed color. So their oxygen fueled car had all these fancy paint job from DuPont because they funded it. Yeah, do you want to add something or? So, okay, so that's obviously chemical. All right, conserving energy resources. So energy resources can be conserved by reducing energy needs and by increasing efficiency. So what do we call it when we use less energy or use energy more efficiently, Milo? Energy conservation. Yes, yes, yes. This is the whole turn the lights off when you're not in the room. So we have 3 R's. Our first R is reduce. What are the others? Chloe. Reduce, reuse, recycle. These are our big ones, right? So these are the 3 R's of conserving energy. I just learned that the half the glass I've been putting in my recycle bin, they don't take. And I'm like, well, I was trying. Yeah, I have to take it somewhere else. I didn't know. I was like, oh, I've been putting it in there for 6 years. Oh, yeah. Yes, Colin. Repeat. Oh, yeah. Yeah. It's like when you wash your hair and it says to shampoo. Yeah. Lather, rinse, repeat. How many times do I repeat? Am I in a constant loop of repeat? Do I just wash my hair ad infinitum? Because there's no, I mean, really. Yes, forever and ever. We had a friend that stayed with us during COVID because his mom worked at the hospital and she didn't want to make him sick. And he stayed with us for 9 weeks during COVID. But this kid's habit is to get in the shower and turn it on and stand there until it runs cold and continue to stand there. This is what he did. He just stood in the shower until it was all cold and he would just stand there. And I'm like, well, that's weird and expensive. But we've warned him that since then we've had a tankless water heater installed. We're like, you will never, ever get out of the shower in this house because it will not get cold. You will just stand there all day, wait for it to get cold, and it will never get cold. Because the way water heaters work, right? You got this big tank, and once you've drained the tank, it hasn't had time to heat. But the tankless ones, it's like the opposite of a condenser coil. Basically, the water runs through heated, like it's heating it as it runs through. So it never runs out, which is nice. It does change your pressure, though. So next week is our last lesson before we do review for midterms. I want to make sure that you guys know that, first let me move this. If you go to your student file, I'm going to show you where this is. I want you to see where this is so that you know, everybody knows. So if you go to your Dropbox, all right, it will look like this right here. That's what your Dropbox looks like, right? Everybody been there at some point? Everybody visited? Yes. So under your resources, you have this little guy here. It says midterms and finals. If you go in there, you will find, if you go to the midterms file, there's one just for you. And in it are multiple resources, including. This is the link for Jeopardy. You go here. It's an actual Word document so that you can click the hyperlink. So you click this hyperlink and it takes you to a website where you can play Jeopardy by yourself. You can play with a friend, whatever, okay? And we will be doing that Jeopardy as our last lab. We're going to divide the class into 2, and we're going to play Jeopardy. Now, you've also got a midterm review where the answers are revealed, meaning that if you're using PowerPoint, you can, if you open it in PowerPoint, as you click through it, the answers will come to you when you click, as opposed to just being able to see them. Whereas if you go to the other one where it says answers visible, there's no clicking. Everything's already there. Because sometimes when you open this, if you don't open it in PowerPoint, you don't see something that's missing. Like if it's not on reveal, you don't see it. So I don't want that to be the case. So if you go and you're having trouble seeing the answers, maybe you're in the wrong one. Like maybe you need to go to the one where the answers are visible. Okay. And the last thing is up here, these are JPEGs of the visible ones. So maybe you're just trying to look at it on your phone and it's a little difficult to open it in like Google Slides or something. These are all the JPEGs of the exact same slides. They're just in JPEG form. So you can thumb through them this way too. Some point today, there it goes. So you can just thumb through these like this on your phone, like riding around in the car or whatever if you're not driving, right? So these are the things that will be covered on that exam. I am considering allowing everybody to have a small note card with formulas because sometimes people can't keep all the formulas in their heads. I will decide by next week if I'm going to let you do that, but it'll be the kind of thing where you have to arrive with it. It has to be 3x5 or smaller, and it has to have writing on it that only formulas, like you can't have definitions or anything else, but just formulas. You can define what, like you can write, you know, G equals gravitational constant or whatever. So you can remember what the letters and whatnot mean. But yeah, questions?
Are we going to labeling the rocks?
So Bailey asked that earlier. So if you look in here, I think the main thing it asked you about was
They just have 3 types of rocks.
3 main types of rocks. Yeah. So I don't think you're gonna be, if I'm remembering correctly, and I will double check all this to make sure before you take that exam, when we do the review, we'll go over everything. Yeah. If you don't see it here or in like here and in the Jeopardy, these are the 2 places to look. Everything that's on that midterm will be covered in one of these areas, if not both. If that makes sense. Does that make sense? Questions? Anybody else have any questions about what to do, what to study for? No, we're all good. I don't try and surprise people with things. Why won't you let me click? I am. Control, click. Anyway. Yeah. So if you have questions about anything like what to study for or whatever, you know, ask me, send me an email, whatever. This is my dude from earlier because it didn't want to play for the other group and I couldn't make their videos work, which was a pain. This is what the Jeopardy looks like, just so you know. And you can set it here by number of teams, right? So if you go to, you know, 1 team or no teams, you can set it there and it'll show you like all your categories are there. And your questions, like you click the question, it'll come up for you and you hit the space bar to reveal your answer, right? That's how it goes. Yeah, I like to move it. Name that scientist. Oh, do we remember names? Ooh. Jules. Prescott Jewel. Spelled wrong. I got to fix that. How did it do that? Anyway, so what now?
Why is it always who is and what is?
That's Jeopardy. That's the way Jeopardy is formatted. So
Answer your question.
why is it spelled that way? Yeah, answer in the form of a question when it's Jeopardy. You ever watch Jeopardy? Anybody never seen it? Yeah, so yeah, you there we go, fix that. So yeah, so you answer in the form of a question. That's just how you do it. Yes.
Is there music?
No. No music. No music. But anyway, y'all are welcome to practice it. By all means, practice it. We got a few minutes. We can throw some up. Who wants to throw one up? What do you want?
That
This one?
Yeah.
Bailey. Bailey gets it. Yeah. What is 1AU?
Can you just add teams? Can you just add points?
Can I what?
Yeah. Can you just add points to the teams without them answering the question?
Yeah, actually you can because let me take that off of there because there you go. You can do that because sometimes I forget and I have to go back and do it. Who's got another one? Colin.
Let's go look at 7 for the machines.
What is
700 for machine. Liam, do you know it?
What is input arm?
There you go. Or effort, either one. Yeah. Input.
Um,
Can I do one? Well, really, effort is better. Yeah, let me get you back to the thing. Whoop. What you want?
900 on Name That Scientist.
Name that scientist, 900. Bing. Chloe. There you go. Yep. Veganer. Good old veganer. All right. Yusuf.
What is work?
Work.
900.
900. There. Okay. All right. Ooh. Colin, you know?
What are distance and
It's something like that. You're almost there. Force and distance. Yeah. So really go over these. Like practice them. If you can practice them before you come to class, before you come to that last review day, that's the best way to do it. Because that way, your whatever team you're on will do well. All right. Do you have another one, Lucas?
You played the video.
Sure. Yeah, I like the IE guy. He was the best. He for real was like loving one.
Yeah, I call him that.
I enjoy that guy. He was fun. Wait, is that yours or the other one? I can't tell. It says in the way. That's you.
Yeah, all of them. After we watched. Oh, thank you.
So we had our hitting the books mechanical energy dude. Oh, see now it's gonna do this thing. Hold on here. Why is it doing this to me? Actually, I have them pulled up over here because they were being weird. Yeah, I had them here too because it was being weird. Yeah, hit the books. Yeah.
I wish I could hang out, but I gotta go hit the books. Okay, let's hang. Yeah. Hang out, but I gotta go hit the books. Okay, let's hang. Yeah. Hang out, but I gotta go hit the books.
He's fun. I like that guy. Oh no. No, it does not want to load. There it goes.
So good. So good. You stick it.
We got Dork. We gotta love Dork.
Oh.
Such a classic.
It's Michael.
Oh no, it's Michael. Go. No.
Man, you're so lucky.
That's Hooks. She's funny.
Why did he do that?
I guess to see if he'd wake up because he cast a shadow on him first, you know? That's my guess. Or maybe the director just said, walk a circle. Could be that.
don't need to insult your city, but the people of this beach are very rude at us. I'm sorry to hear that.
Poor guy. Poor guy. Poor guy. This was actually a different potato battery. But it's the same idea. He's spoiled. Ooh, a penny-sized hole. And stick in a penny. Squish. And a nail.
It's called galvanized nail.
Mm-hmm.
How long would the
Added
potato battery last? Depends on how big the potatoes are.
Yeah.
Bigger the potatoes, the longer.
Mm.
How are you not getting the electrocuted right now? Like,
The soaking stuff.
Yeah, it's not no circuit.
what? Yeah. Gotta complete the
You gotta go all the way. There you go. Ding ding.
circuit.
Woo!
More potatoes.
Why is that there?
Seen that like Mark over
Fondue
where he did a
potatoes.
lemon batter.
Ta-da. Yeah, those are so fun. Let's save. That's the best. Save for last. That's the best. Yeah.
Because of your many years as a nuclear technician, we're putting you on a nuclear salt.
I don't know what's talking.
It's pronounced nuclear.
Hush.
Nuclear.
Yeah.
Is this the falling? I lost the falling, huh?
Instead of what runs for
Yeah.
your life.
No, it's not that.
Yeah.
No. What in the world? Homer Simpson.
Facility.
I really wanted to do this with somebody. This just looks like too much fun.
Do you think that selling your nudes online and
What?
Thanks.
No. No.
you think that selling
Jeez, dude.
Come on, man.
It's big account. I don't know where it's coming from. I guess people who like this like that. I don't know.
Has to stay though.
I'm sure.
I think that's the guy who told them that they should do that. 'Cause
He's trying really hard on the
I've
left.
played before.
The other classic elastic potential energy videos are the ones with the cats and the rubber bands. Like, but too many people like cats and would be offended if I showed the cat getting snapped. So I showed full-grown men instead. So you've seen the cats, right?
So much.
That one and the kid that sounds like Cartman, but he swears, so I can't.
All that. Oh,
I'll show you the cat.
I laughed for no joke 30 minutes.
Let's do it.
I know it's too much.
Oh, the kid who sounds like Cartman. That kid is.
Cartman's hilarious.
I don't know why cats. I don't know why. Is well, they're all good. The fourth one. This one? Oh yeah, this one's a classic. Yeah, this poor cat. There's plenty of them. Like people give their cats rubber bands, knowing this is gonna happen. It said, "Oh, poor baby." Oh.